Hey folks, we're going to continue with our intro for simple harmonic motion, and I got an example for you. So first of all, if you got a sec, I would copy this diagram down, and all it's supposed to be is a mass on a spring bobbing up and down, and it goes to, this is the max height it goes to, and this is the lowest it gets to. The center point here, that's our equilibrium position. That's where it would be at rest if it weren't moving back and forth at all. Okay. All right, so I'm going to kind of continue where I left off in the previous video. The last thing we wrote was A is equal to negative omega squared x. So why is that important? Okay. Well, it turns out that if you know the linear restoring force for the simple harmonic motion, it turns out that you can figure out the period of the simple harmonic motion. So for instance, last year, when you folks had Phys 1, you might recall that the period for a mass on a spring was 2 pi root m over k. So where on earth does that come from? Right? It's just some random equation that they came up with, okay? Well, no, okay, it comes from this, okay? It comes from knowing this relationship. Let me explain, all right? So we know that the force acting of a spring acting on the mass is negative kx, right? And we also know that on the mass, net force equals ma, okay? Now, it turns out in this problem, if you measure everything from equilibrium, you can ignore gravity acting on the mass. In class, I will talk about that, and I'll provide you with like a handout that shows you mathematically why that is. But basically, you can ignore mg in this case. And so like when the mass is like up here somewhere, the only force acting on it you can pretend is a spring acting back toward equilibrium. And when the mass is down here, you can pretend the only force acting on it is the spring trying to bring it back towards equilibrium. Okay. So these both describe the force acting on the mass. So I'm going to set them equal. So you got ma equals negative kx. And we're going to get the equation, we're going to get a by itself. So a is equal to negative k over m times x. Okay. So we have a in terms of x. Okay. Whatever's in front of the x is negative omega squared. So omega squared is k over m, okay? And so omega is root k over m. And you might recall that period, and I kind of wrote it this way, omega is 2 pi over the period. Therefore, the period has to be 2 pi over omega. So check this out. Period is 2 pi divided by root k over m. And if you simplify that, you've multiplied both numerator and denominator by root m over k, you get the equation that you memorized last year, okay? So that's how you get the period of a mass on a spring. Now, that's a very simple example. We're going to do a bunch of examples like this. So you have to actually know the process, okay? So the first step is to get a in terms of x. The second step is to realize that period is 2 pi over omega. And the third step is once you get a in terms of x, whatever's in front of the a is omega squared. Okay, so it's kind of like a three-step process. Okay, and we're going to do that with several systems, and you're going to do that when you're trying to work on problems and solve and ask, answer questions like what's the period and frequency of this thing bobbing up and down, left to right, or swinging back and forth. Okay, so that's the idea. All right, now the other thing I mentioned to you is for our position equation, we had this, x equals a cosine of omega t plus phi. Now, by the way, you could use a sine function here as well, and I'll explain that too in a second. Well, this phi is just your starting condition. So let's say this thing is bobbing up and down, and you start your watch when the block is all the way at the bottom, okay? Well, that means x is equal to negative a. Okay, so how do we make this equal to negative a? Well, you have to make cosine equal to negative 1. At time equals 0, this whole thing equals 0. So what does phi have to be? so that cosine of phi equals -1? Well, phi has to be equal to pi. Cosine of pi, which is the cosine of 180, is -1. So in that case, your phi would be pi. Okay. What if, on the other hand, you started your watch when the mass was moving upward through equilibrium? Okay. Well, in that case, so that's when t equals 0 now. We're starting a new trial, and you start your watch there. Okay. Well, again, omega t is going to be 0. We want our position to be 0 because we're at 0. So cosine of what angle is 0? Well, here you've got two options. You've got pi over 2 or you got 3 pi over 2. So which one's the right one? Well, you have to look at it and figure out, like, later on, my position will be positive. Immediately after this 0 time, my position will be positive. So let's try pi over 2. So cosine of pi over 2 is 0. If I go a little time later, this whole thing will be a little bigger than pi over 2, which will put us in the second quadrant. And if we're in the second quadrant, cosine is negative in the second quadrant. Well, we need cosine to be positive because we have a positive position up here. So this doesn't work, so this would be your answer. Okay, so that would be your phi that you would put in there. Okay, if you put 3 pi over 2 in for here, at time equals 0, cosine of 3 pi over 2 is 0. If you add a little bit to 3 pi over 2, well, now you're in the fourth quadrant, and cosine in the fourth quadrant is positive, and that's what you need for the time immediately after 0. Okay. The other thing too is, let's say you did a sine function right there. Okay, so let's say you'd said, instead of cosine, you wanted to use sine, so you do a sine of omega t plus phi. And let's say that you're doing the same spot. You're doing the mass as it moves up through equilibrium toward the top of its path. Okay. Well, sine of what equals 0? Well, this could be 0, or this could be pi over or pi, right? The cosine of 0 and the cosine of pi is 0. Which one is it? Well, let's start with 0. Okay, so if I put 0 in there, then if I go any time later, I get a sine of a really small number, which would be in the first quadrant. And sine of something in the first quadrant is positive. So 0 would be your phi in this case. Okay, so you kind of look at the time when time equals 0, and then when time is just a teeny bit bigger than 0, like what happens. Okay, now let's see what else here. I do have one example to do with you, but I think I'll save that for the second video. Oh, I will make one general note. Phi for the sine function is always equal to phi for the cosine function plus pi over 2. So for instance, over here, we had the 3 pi over 2 for our cosine function for that spot. If I add pi over 2, I get 4 pi over 2, which is 2 pi, which is also 0, right? So that's where that's another way to look at it. Okay, so it's like a phase shift. All right. So I'll do the example in the next video. I hope that was helpful, and thank you very much.